Hello again. In this segment, we're going to be talking about torque and angular momentum, and this is a lead-on from our previous segment on center of gravity and its effect on motion of bulky objects. Okay, now so far we've been talking about a very, very simple situation. Let's suppose we have a spherical object. It's not quite a sphere, but it has a center of mass located there. And let's suppose we apply a force to that, F. By Newton's laws, we're going to set that body in motion, and we're going to be imparting momentum to that object. And if we apply the force in line with the center of mass, the momentum imparted to the object will also be in line with the direction of force. So a short time after we impart the force to it and impart momentum to it, our object will look like this, and the center of mass will be located there. This is supposed to be the same size, and that center of mass will have momentum. Now let's do something a bit more complicated. Forces don't always line up nicely with the center of mass. So let's take our object again. I'm going to make it a little bit bigger because I want to have some details in there. And let's say that we have a center of mass right here. But now, instead of applying the force directly in line with the center of mass, we apply the force up here somewhere. Well, obviously we're not going to have the nice simple translocation, or what's called translation, of this body by this nicely inline force. Instead, the force is going to be acting through a point right there that's located some distance from the center of mass. This distance right here, this object right there, has a special name. It's called the moment arm. And the force in this instance is going to be acting through the moment arm. Now, there's inertia that is embodied in the center of mass, but there's also inertia that is embodied at the point where the force is acting. And when that happens, you're going to have two things operating. You're going to have some translational motion there, but you're also going to have a rotational motion imparted to this. And so if we put a little mark, for example, on our object, and we look at it a short time later, it's going to look like this. It's going to be the same size, unlike our previous mistake. The center of mass will be right there, but now our mark is going to be right there. So not only has there been a translation of the center of mass, but there's also been a rotation of the object as well. Now, when you have a force that's applied out of line with the center of mass of an object, you've applied a so-called torsional force, and the force you get out is called torque, T-O-R-Q-U-E. And we'll speak in a moment about how torque relates to the kinds of kinetic energies that you get out of setting objects in motion. But the main thing we want to talk about right now is that inertia in this instance occurs in two different dimensions. You have translational momentum, that is the momentum that's imparted to the center of mass, and you have so-called angular momentum, which refers to how rapidly the mass embodied in the bulky object is rotating about the center of mass. Now, there's some complicated mathematics that we can use to be able to describe this. We're not really going to go into that in any great detail. It's most important to realize that when you're talking about momentum of real objects, usually there's some combination of translational momentum and angular momentum that is imparted to those objects. And there's some fairly simple intuitive rules that you can apply to this, and again, you just need conservation of momentum to be able to understand what's going on. If you are curious, then you can get into the mathematics of it so you can analyze it quantitatively, but we don't need that to be able to really understand intuitively what's happening. So let's take the motion of a body. And again, we have our center of mass right there. And let's say that we have a force acting in line with the center of mass, just like we had before. Okay. All the momentum that is imparted to that object is going to be translational momentum. So if we draw, let me just get my right color here. If we draw this momentum as a vector, the translational momentum is going to be an arrow of a magnitude that's proportional to the momentum. In this instance, there's going to be no angular momentum because you've had no moment arm or force applied through a moment arm to set the object spinning. And so if we build a table for translational momentum or angular momentum, all the momentum is going into translational momentum and none of the momentum is going into angular momentum. Now suppose we take our object. And again, this is supposed to be the same size. Use your imagination. Center of mass there. And now we apply a force to this point right here. And in this instance, we have a short moment arm. What's going to happen then is that you're going to have a small angular momentum applied to this object, but you will have a large translational momentum. So if we continue with our table here, we'll have less translational momentum, but we'll have some small degree of angular momentum. Why? Because we have the force operating over a short moment arm, and the amount of angular momentum that's imparted depends upon the length of the moment arm. Let's now take another object, again, same size, center of mass there. But now let's make the moment arm the edge of the object. We apply the force at the edge of the object. The moment arm is the radius of the object. And what's going to happen then is that all the momentum is going to be angular and none of it is going to be translational. So if we continue our table right here, all the momentum will come in the angular form. Now there's this conservation of momentum. There's a certain force that's being applied to this. This is imparting a certain momentum to the object as a whole. But depending upon where the force is applied with respect to the center of mass, you can get varying combinations of purely translational motion, purely angular motion, or a combination of angular and translational momentum. And this will be important when we talk about the movement and motion of real objects that you find in the real world. Okay, well, that's all for now, and we will see you in another segment.